All right, thank you so much for your kind introduction. I will try to share my screen. Can you see the screen?
Yeah, we can, yeah.
Okay, very good. So anyway, we really like to thank the organizers for their kind invitation to this very interesting series of webinars. And today my presentation is addressing some topics in signal processing, reinforcement learning, and waveform optimization for multi-carrier joint radar communication systems. And I'd also like to acknowledge my co-authors that have been contributing to the examples I will be presenting, namely Petteri Pulkkinen, Maria Pikaf, Volker Keskin, Henk Wummers, Tuomas Aittomäki, Juha Chui, Ubli Mitra, and Salil Sharma. Here's a brief tasting menu of today's presentation. I will first consider some of the topics related to cooperation and co-design of radio frequency sensing and communications. And then I'll describe a few ideas on multi-carrier models for integrated sensing and communications. Then I will present some examples of waveform design and waveform optimization for joint sensing and communications. Then I will address some topics on model-based reinforcement learning and online optimization in ISAC and different tasks, so sensing and communication tasks in ISAC. Then I will briefly address the topic of interference management in ISAC using interference alignment principles. Finally, the last technical topic is dealing with signal processing in ISAC system. And the key idea there is that many of the non-IoTs and impairment that wireless communication systems are experiencing can be actually exploited in the radar sensing part. And I will present two examples how to take advantage of the intercarrier interference as well as phase noise in the radar task of ISAC. And I have quite a few examples, so the gory details in these examples, they can be found from the publications. I will take an effort to convey the intuition and basic ideas, but the fine detail and most of the equations can be found from the papers. This describes some of the scenarios that we are considering in joint sensing and communication. So we have scenarios where the radio systems are just sharing and coexisting in the radio spectrum without any cooperation or being co-designed for mutual benefit. So in that case, there will be no sharing of channel state information, interference awareness, and so on, but everybody works just on their own. And when the systems start to cooperate, then obviously there will be exchange of information, feedback, feed forward, and also they may know their waveforms and protocols and use those in order to improve the performance in each task. And of course, then there may be also scenarios where you are dealing with non-cooperative system or even adversarial systems that try to make your life miserable, and then there may be some intentional interferences present, whereas in just sharing and cooperative scenarios, there are some unintentional interference that you may have to deal with. In integrated sensing and communications, the cooperation and co-design of the sensing and communication is used for mutual benefit. So all these participating subsystems somehow gain from that cooperation. This will lead to more efficient use of spectrum and power resources. And as a result, these radios may be operating in shared, congested, or sometimes even in contested spectrum. One of the technologies needed here is multifunction hardware, and so-called RF convergence is kind of one of the research trends towards multifunction hardware and shared transceiver and antenna resources in a platform. Integrated sensing and communications, as this community well knows, will be one of the truly novel technologies in the upcoming 6G wireless systems. It's something that is very different from 5G, so it won't be just more of 5G, but it's something really new in the wireless standardization. It will provide us also very exciting research opportunities in information theory, signal processing, computing, radar systems, vehicle technology, as well as in hardware and circuit design. It's not enough just to understand wireless communications in this context, but one also needs to understand RF sensing and radar tasks, because it's the other part of the job. And in my presentation, I also try to convey those radar ideas to this context. There are a variety of important applications for this technology: vehicular networks, environmental monitoring, remote sensing, IoT, smart cities and smart grid, and well-being and vital sign monitoring, gesture recognition and user interfaces, gaming, localization, sports analytics, and even some safety and security applications. And here are a few examples of the applications. So there's just a joint radar communication platform there, and then user interface requiring both communication and sensing. Then more conventional radar that is a multifunction radar that can also perform communication at the same time. And the lower left corner, there's an example where we actually used regular cellular radio systems to capture the micro Doppler caused by breathing and chest motion and heartbeats and so on to monitor vital signs. And then, of course, one of the most interesting cases will be this vehicular applications where you do both sensing and communication simultaneously. In ISAC system design, the communication sensing subsystems, they have a number of degrees of freedom and operational parameters that can be adjusted in order to optimize the performances. The objectives may be something like sum rate in communication, constant force arm rate detection, or parameter bound in the parameter estimation. There are quite a few technical challenges that we are facing, one of them being the dual function waveform design. Then since we are dealing with the radio environment where you have many systems working in the same spectrum, then interference management is crucial. And for sensing purposes, high resolution capabilities in space, time, and frequency domains are usually necessary. Because of these multiple radio systems, one also needs to deal with multi-user and multiple access issues, and also come up with the protocols and ways to share awareness about the state of the spectrum, channel states, interferences, and so on. Also, since there are multiple systems there simultaneously and multiple users, one needs to address problems in resource allocation, scheduling, and so on. The sensing task that we are handling, there's a variety of objectives for those tasks. And those objectives are of course, important to understand when we do joint optimization of communication sensing. The sensing usually requires design of probing waveforms, and in order to do that, one of the radar technologies called waveform diversity, how to use different types of waveforms for different tasks and how to adapt those waveforms. One typical property for radar sensing waveforms is ambiguity functions that allows you to distinguish between targets with different delays and different Doppler shifts. If you need to launch multiple waveforms at the same time, then orthogonality is very important because it allows you to resolve those different waveforms at the receiver. Many sensing tasks are subject to unwanted returns. That's usually called clutter, and you wish to design sensing systems that are resistant in the face of clutter. And since the radio environment is very dynamic, you also need to come up with techniques to adapt and learn based on that, based on the awareness on the dynamic radio environment. Just to remind you that there are quite a few different radar tasks, and each of these tasks has different objectives and different optimality criteria. And so these tasks include target search and detection, determining target range, velocity, and bearing. Then once you have a detected target, you may have to track it, and then you may have multiple targets that you have to track simultaneously. And these targets may be maneuvering, moving in certain ways, and you need to also deal with these maneuvers. You may also want to characterize the target and estimate certain parameters of the target. And channel estimation is usually one of those tasks that it may capture the target radar cross-section, for example. And then in order to come up with a reliable detection and estimation performance, you also have to estimate noise and interference statistics. And that allows, for example, you to control the false alarm rate in detection tasks. Target recognition is also one important task. It may be based on high resolution range profiles or microdoppler signatures, for example. And in this type of multi-radio system environment, then mitigating interferences and then optimizing power allocation and so on is very important, so that you get the desired performance, but you are not causing too much interference to the other cooperating or non-cooperating radios. Since these joint radar communication system, ISAC systems, they are actually multifunction systems, then managing this multifunction operation is important. So it includes scheduling, for example, how to track different targets and how much time to spend and when to use sensing and when to use communication, how much time spent on the different sensing and communication tasks, and how to allocate power resources, antenna resources, and so on for different tasks. And I already mentioned the problem dealing with some unwanted returns, multipath, and different non-IoTs on intentional and intentional interferences. In certain tasks, also polarization is very crucial, one of them being environmental monitoring and weather monitoring. So for example, if you want to figure out if there's a lot of rain or humidity, then polarization is certainly an important issue. Also, if there's a need to detect the changes rapidly, so any change in the radio spectrum would be somehow detrimental, then you may wish to apply some techniques for change point or anomaly detection. And here are just some examples of these different radar sensing tasks. So on the left there's a MIMO radar, and then next figure there's a distributed detection of targets, where based on the diversity order, the kind of slope of the probability detection curve improves. And then, of course, this type of a very typical application of vehicular sensing and of other vehicles. And then on the upper right corner, there's a microdoppler signature of human breathing and heartbeats, and then that could be used for vital signs. On the lower left corner, there's a radar target recognition based on high resolution rates profiles and acquired by MIMO radars. And the next figure, there are maneuvering target trajectories that you could kind of track. And then there's an example of beamforming and interference cancellation in the radar and so on. So these are very typical radar tasks, and then the performance criteria in each task would be slightly different. And when you jointly optimize sensing and communication, that certainly plays a role when designing this system and its objectives. Okay, so let's move to multi-carrier waveform design and optimization in ISAC. So, of course, multi-carrier waveforms, they are used in most current and emerging wireless systems. So 4G, 5G, digital TV systems, digital radio system, Wi-Fi, and then probably 6G in some sense at least. And some of the NOMA technologies also are based on multi-carrier models. Multi-carrier models, there's a very nice paper by Wang and Giannakis where Fourier meets Shannon. So it's since I like the paper a lot, I wanted to point out and recommend reading it. Multi-carrier waveforms are also considered for radars, and they are OFDM-based radars. Already in 2001, there was a paper or a series of papers on multi-carrier radar called MCPC, which uses polyphase codes, and it's kind of like a multi-carrier CDMA type of radar. And then obviously most passive radar systems, they also use multi-carrier signals, even though they are not actively producing those signals themselves. We also did a few years back some work on generalized multi-carrier radar, basically in part inspired by this Fourier meets Shannon paper with my former student Maria Pika, and can generate a matrix model for multi-carrier radar that has this variety of different waveforms, frequency hopping, OFDM, MCPC, multi-carrier CDMA, linear frequency modulation, and so on as a special cases. And just by filling in these matrices appropriately, generate these models. And the reason why people are considering multi-carrier radars is that it's nice benefits in terms of frequency diversity. Also, you can avoid jamming or interferences easily by allocating powers to those subcarriers that are not experiencing such interferences. Resource allocation. And then one of the benefits is that you can actually estimate a Doppler from single pulse because you use multiple subcarriers. And these multi-carrier signals, they also tend to have a rather broad bandwidth. And as you may know, that the range resolution basically depends on the RMS bandwidth of the radar signal. One additional benefit is that there's really a lot of work on hardware designs for multi-carrier systems, and a lot of that work can be exploited also in the sensing and joint sensing and communication context. Obviously, there's no free lunch, so one of the key drawback of multi-carrier waveforms is the high peak to average power ratio, and that may prevent you from using your amplifiers very efficiently. And since the radar signal to noise ratio basically depends on the range to the power of 4, it may reduce the coverage of the radar part of this joint system quite a bit. It's very common also to combine these multi-carrier models with the multi-antenna configurations that leads to MIMO OFDM type of models, and of course multi-antenna systems give you then this spatial degree of freedom, and you can resolve targets in the angular domain. And here are just some examples of multi-carrier design. So on the upper right corner, there's this MCPC, which stands for multi-carrier base coded waveform design. So it's basically a multi-carrier CDMA model where these codes are designed in a particular way, and this is a model proposed by Lebanon. And then on the lower left corner, I have two examples. Just a conventional multi-carrier CDMA, where the spreading is done over frequency, and then multi-carrier direct sequence CDMA, where the spreading is done over time. And there are just some examples how to produce very commonly used waveforms using this type of generalized multi-carrier radar model that we have proposed. So this up and down chirps or step approximations for those, and then conventional frequency hopping waveform given in figure. We developed this generalized multi-carrier radar model and derived some transmitter and receiver equations for such a model. And just by filling in these matrices appropriately, you can create many of the models that I presented in the previous page. Here on the right, there's an example where we basically use multi-carrier DSCDMA model for this joint radar communications. And so you allocate certain number of subcarriers for communication part. And then you could use, for example, orthogonal variable spreading factor coding for this communication subcarriers that could give you different data rates and so on. And then for the radar part, you could use then any good radar code. And then we, based on the ideas that are used in 3G wireless systems, we would use, or we are using long scrambling codes to isolate the communication part and radar part from each other. In this particular design here, we have now the radar subcarriers on the edges of the band. So it would give you a larger RMS bandwidth and as a result, a better range resolution. And here on the lower right corner, there's an ambiguity function for this type of joint multi-carrier DSCDMA waveform with these scrambling codes. So you can see that it looks almost like an ideal thumb-back ambiguity function. So it gives you basically a correlation over delay domain and Doppler domain, and it has this close to ideal thumb-back shape, which is something that one would desire from a radar wave. So then once you have this multi-carrier model, then you can, of course, optimize these waveforms for the current channel and interference scenarios. And these optimization problems, they can be written so that they are either radar-centric. So the idea is to maximize the radar performance under constraints on minimum tolerable performance for the wireless data transmission. So for this data transmission, of course, data rate or sum rate or quality of service are typical criteria. And radar part, of course, depends on the radar task at hand. Then if the design or optimization is communication centric, you would maximize the communication performance. Again, you could use sum rate, mutual information over some of the quantities I mentioned above. And then you would impose constraints on the minimum tolerable radar performance. And then, of course, there's an option to do multi-objective optimization or Pareto optimization, where you have these two, both radar and communications in the same objective functions, and then you find some kind of a Pareto optimal solution for the problem. So here on the right, that's just a kind of a prototype problems for this waveform optimization. For example, in the radar-centric case, you could maximize the probability of detection under constraint on the false alarm rate. So that would be a classical Neyman-Pearson detector. And then you would have a constraint on the desired data rate for the communication users and some kind of power budget, that how much total power you can use. In a target parameter estimation problem, you would minimize the Cramer-Rao bound, and then again apply constraints on the desired data rate for the communication users, and then you would have a total power budget for the radar, and you might also want to apply constraint on the subcarrier power ratio, so that you could spread the power a bit broader in the over the whole bandwidth, and as a result, get better RMS bandwidth and range resolution. So there are a variety of objectives for the radar communications part, and then of course also a variety of constraints. Some additional constraints people often consider is this constant modulus property that would allow you to use the amplifiers very efficiently. Then you may wish to have certain shape for the radar ambiguity function. So you could describe some properties of the ambiguity function, or departure or penalize for the departure from certain prototype shape of the ambiguity function. Then if you have to launch many waveforms simultaneously, then you might want to impose constraint that ensures low cross-correlation among MIMO waveforms. And then you may have per antenna power constraints and constraints on the beamformers, or if you do, for example, beam space processing, you may have some constraints on the beams. And just to give you an example, this is a old piece of work that we did quite some time. So the radar-centric objective function is to minimize or maximize the detection probability under false Olin rate constraint. And then this Shannon-Hartley formula, kind of making sure that you get them at least a certain minimum rate for your communication, and then there's a power constraint. And this type of problem would be non-convex, and as a result, you need to come up with ways to solve the problem or do some relaxations. This type of detectors are based on likelihood ratio tests usually, and then you have to derive the decision statistic for the detector under null and alternative hypothesis. And so we basically did that type of derivation, and for that Neyman-Pearson type of objective, and you in this case it was a gamma distribution approximation of the test statistic, and then with these false alarm rate constraints and so on, the tail probabilities and so on. An alternative criterion that we used here was based on mutual information, and mutual information is nice in a sense that it usually leads to convex objectives and allows you to use convex optimization techniques. And in this case, when we used also mutual information for deriving the detector, and of course the detector has a slightly worse performance than the Neyman-Pearson detector that is optimal, but the gap to Neyman-Pearson is very small, and actually almost infinitesimally small. And at the same time, solving this problem with mutual information is convex and much faster to solve. But obviously, it does not guarantee similar false alarm rate control as the Neyman-Pearson detector does. And as a result, especially in radar applications, that if you get too many false alarms, it may overwhelm your radar. The power allocation that came out as a result looks actually like a water filling solution. So this is the kind of power we use for the radar part here, and obviously that looks like a nice and intuitively makes sense that you put power on those parts of the spectrum where the signal propagates well and there's no interference. Similar example is here to minimize the Kramer-Rao bound for target parameter estimation. And again, there are a bunch of constraints, power constraint. Then we have a kind of also a per subcarrier power constraint that is imposed by the rate constraint for the communication system. So our radar is allowed to use a certain amount of power for certain subcarriers to make sure that the signal to interference noise at the communication part remains sufficiently high. And then we have an additional constraint that basically spreads the power and on broader bandwidth, and so it tends to allocate power more on the band edges to give this higher range resolution. And in case of frequency selected channel, we came up with this type of expression. And if you look at these figures here, that this solid red curve here is the per subcarrier power constraint imposed by the communication system. And then this communication channel gain is this dotted curve here. And in that communication channel, then of course communication system will put more power on those subcarrier where the gain is high. And of course, as a result, the radar would use less power or no power on subcarriers. And where the gain of the communication channel is very low, then the radar can use more power, and the power constraint is there also that the subcarrier power constraint is more relaxed there. And then the outcome of this waveform optimization, then the ambiguity function of that waveform is given here below. Okay, so those were kind of very classical examples how to optimize these multi-carrier waveforms, and also a lot of other people who have worked on this type of problems, and you may have different objectives and different constraints and so on, and then usually you come up with unfortunately with non-convex optimization problems, and then you have to go to your bag of tricks to solve those problems efficiently, so that the solution would be there in timely manner. Then instead of optimization, one could also think of using reinforcement learning for waveform optimization, and basically learn through exploration and exploitation which waveforms to use and how to design these waveforms so that the job gets done. This, of course, this reinforcement learning problems are usually formulated so that there's an agent that is interacting with its environment through actions, and then the agent is able to observe the state of the environment, and also gets some kind of scalar reward for the state that it's observing. And then this reward is usually describes what's important for this agent. For example, in our case, you would get a reward for high data rate or close to optimal parameter estimation or detection performance. Since we are dealing with the physical world signals, then of course our observations will be noisy, so we don't get accurate information from our environment. And therefore we usually say that these models are partially observable models. So these models obey something called partially observable Markov decision processes. Of course, wireless communication systems and radar systems, they are man-made systems. There's a lot of structure there, and also we, as wireless engineers and radar engineers, we know what's happening in the radio spectrum. So we have understanding of the physics of the radio spectrum, how the radio waves propagate, interact with the environment, and we have done our homework in terms of Maxwell equations. And we want to take advantage of this kind of knowledge that we have acquired. And therefore, we have taken the approach of something called model-based reinforcement learning. And that is basically comprised of classical reinforcement learning, but then there's a separate part that basically learns the model of the environment, and that is then used in the kind of designing the policy for the reinforcement learning and choosing the actions there. So you could think that there's a model-free reinforcement learning plus a model learning part that learns how the environment, for example, behaves. You could also think this as a control engineering problem, that you have basically a controller here that is using based on reinforcement learning, but then you have a model learning part that learns the plant model, for example. So based on the plant model, then your reinforcement learning will design the optimal control in a sense. All right, so, and of course the difference to, well, all reinforcement learning, they basically learn continuously and autonomously improve their performance. But the difference is that we actually exploit now the domain knowledge. And just like in any reinforcement learning problem we have, is exploitation and exploration parts. So exploitation takes advantage of the best resources we have, and then every now and then we need to check if there's something better that could improve our performance significantly. All right. So we have now this part that learns this model, and then we have basically optimization problem based on this learned model. We choose the optimal action. So that's basically the control part of our problem. And well, this is a bit busy slide, but it's just that it gives the idea that we are using this Markov partial observable Markov decision process model, and then we learn this probability model of the dynamics of our environment. And in this case, it would be dynamics of how the channels and interference behave. And so we could basically predict how the channels and interferences behave. And then based on that learned model, then we could solve this type of predictive control problem. And so we have basically like an estimated model or learned model, and then we solve a control problem and choose optimal actions based on that. And the action space here is that we select the subcarriers for both for communication and sensing, and allocate powers to these subcarriers. And this internal state of the system is basically described through channel gains and interferences in each sub-channel. And then the observations are basically our noisy observations both for the channel and spectrum states, and also we get some of that information through feedback. The feedback is always subject to error, quantization, or it may be just because of delay, it may be slightly incorrect. In our learning approach, reward of course tells what's important, and now the reward is associated with the communication and sensing performance. But since we want to make sure that we obey these or honor these constraints strictly, we are using something called constraint regret, which basically says that we don't get any reward if we violate these constraints. And so here's an example that we have basically subcarriers on the spectrum, and then time instances, and these green kind of subcarriers are such where we could basically make sense to use the spectrum, and then we basically choose those subcarriers and allocate powers to those subcarriers. And then, of course, every now and then you make incorrect decisions, and you think that the spectrum cannot be used for sensing or communication, and then you can miss the opportunity, and you can, of course, penalize that. Or if you incorrectly think that the spectrum is idle and you use it either for communication and sensing, but it's being actually used, then you will cause collision and retransmissions and so on. So we studied how the regret, which is the kind of cost of learning, how much you kind of have to pay for learning, instead of, for example, if you would know everything, you would Genie would tell you always what's the right thing to do. And usually it's thought that if your learning does a good job, the learning should be sublinear, so kind of way below this kind of linear regret. And in the optimal case, it should be logarithmic. And this solid red curve here tells how our kind of model-based online learning system, how the regret behaves, and it looks very good. It's decidedly sublinear or looks even logarithmic. And then we have also, in this case, we have like quasi-stationary interference. So during the observation period, the interferences remain the same. And in lower case here, we have a dynamic interference scenario. So the interference statistics change more rapidly, and still the regrets are here described by this blue curve. They are still sublinear, but probably not logarithmic anymore. Of course, doing analytical work in this type of dynamic scenario would be very, very difficult. So in such case, you can only do simulations and verify these things. And we see a lot of opportunities in applying the reinforcement learning for this joint radar communication optimization, because the environments are maybe hard to model, so there's some modeling deficit there. And also may be hard to find structured optimization algorithm to solve those problems in time. So by trial and error and using this contextual information, you could learn things. And we've done work on this subcarrier selection and power allocation I just explained, and some time batch management for multifunction radio frequency systems. And in that case, we were tracking targets and so on. And then also antenna selection using multi-banded modeling, and also some work on multi-agent reinforcement learning for flexible spectrum use. Then briefly, I will describe some work on interference management in ISAC systems using interference alignment. So this is a joint work with Johan Chui, who's one of the organizers of these seminars. So the idea is that we will use the interference alignment principles of Jafar to kind of reduce the interference for communication and sensing tasks. In order to do that, we need to have knowledge and share knowledge about the channel state and interferences, and then and that information can, of course, be obtained through feedback from our cooperating nodes. Of course, in a co-design system, the same information is available both for radar and communications. And of course, at the receiver end, you typically have to also estimate these statistics. You can also, if you are using the same frequency resources, you can also rely on reciprocal channels to get such information. And since you have this information, then the idea is to decide precoder and decoder so that the interferences are basically projected into very low dimensional subspace. So the basic idea is, of course, that if you have a radio transmitter and then it's causing interference to either receiver, then the receiver would like to steer this interference into its null space. And then you design this kind of decoder so that it will align the interferences for all J transmitters into this low dimensional subspace. So you kind of create a subspace that is like an interference junkyard, and you want to steer these interferences from different transmitters to that junkyard. And then you can also, just to make sure that you get the desired degrees of freedom both for communication and sensing part, you can impose a constraint on the degrees of freedom, and that will be visible as a rank constraint in the optimization problem. And then you can basically find these precoders and decoders that do this interference alignment by doing optimization in an alternating manner. So you first design a decoder, then precoder, and you alternate this until it converges, and then as a result you will get to sense or communicate almost in interference-free channels. And then of course you will lose some of these degrees of freedom because of these interference alignment. So the interference alignment constraints are given there. So this null space idea is the first expression, then this rank condition there. And then the objective is then to maximize the signal to interference noise and noise ratio. Then this objective function is given here. So you maximize this expression with respect to precoder P and decoder Q, and with this rank constraint. And just to give you some idea what it basically means, that of course typically when you increase the SNR, and that of course typically means that you increase the power, then it doesn't really, if you don't do anything, it basically also means that all the other users will be experiencing more interference. And by doing this type of precoder decoder design, that by increasing the SNR, you would also improve the signal to interference and noise ratio. Whereas if you don't do anything, then the signal to interference noise ratio might actually get worse, and that's the idea with this design. So this blue curve is this our design. So by increasing the SNR, you increase the SINR as well, whereas the competing solution based on this single value based precoder, the increase in SNR does not improve the SINR. And here are just then some probability detection curve as a function of SNR for this precoder decoder design, interference alignment based design versus this same SVD based precoder. And the performance gain is very significant. The last item is dealing with the signal processing relate in the joint radar communication systems, and with the particular idea that you can take advantage of the impairment and non-ILTs that usually are causing a headache to you, or especially in communication systems, and then the radar system actually take advantage of those impairment. And this is a joint work with Volker Kesking and Henk Vermeurs from Chalmers, and Henk will be presenting some of his work later in this seminar series. All right, and two particular impairment that we are considering is intercarrier interference and phase noise, and we use those to actually improve the radar task performance. So intercarrier interference, that's of course caused by mobility, and of course mobility leads to Doppler, and that intercarrier interference is detrimental in the sense that it basically spoils the orthogonal among the subcarriers in the OFDM or multi-carrier systems, and it will also lead to a degradation on the OFDM-based radar process. So here on the right, we have the range profiles of OFDM-based radar with we have two velocities, so 0 or the case of no velocity, and then 50 meters per second velocity with this blue dotted curve. And you can already tell that you could pick only the kind of strongest target there, but the weaker targets would be masked here because of these side lobe levels grow so much. So and in this case, you would totally miss 2 out of 3 targets, and then the idea here is that we will actually take advantage of this intercarrier interference to detect all of these 3 targets. And of course, intercarrier interference becomes more and more severe as the velocity of the targets or relative velocity between the real radar and targets increases. So what we have developed is like a 3-stage delayed Doppler angle estimation algorithm for MIMO OFDM radars in the presence of intercarrier interferences. And what this algorithm basically does, it both mitigates the impacts of intercarrier interference and also exploits them. The mitigation basically leads to improved detection performance, and the exploitation basically improves the delayed Doppler angle resolvability. So none of the targets will be masked in the sense you can resolve targets that would otherwise remain invisible to you. And it will also push the maximum unambiguous Doppler higher level. And what this technique basically does, it works in 3 steps. So you first observe that the spatial covariance matrix, since it's a multi-antenna system, it's independent of target delays and Dopplers, and then we could use that to estimate the angles of arrival for these targets. For example, using the high-resolution music algorithm. Then for each of these estimated angles, we can formulate a radar delayed Doppler estimation problem as a kind of joint carrier frequency offset and a channel estimation problem. And that is used solving so-called SPS algorithm, which is amplitude and phase estimation algorithm by Petr Stojka, and it's basically a beamforming approach for solving this problem. And then in the third stage, here on the right, the delay and Doppler of each target is recovered from this target-specific channel estimates over time and frequency, and basically means that you have to do least square estimation and do the FFT process. Also here I try to illustrate these stages a bit more. So first we have a kind of like a data cube. So we have a space and fast and slow time samples of the data, and then based on the spatial covariance matrix, we can do this angular domain estimation. And then for each of these angles, we do this carrier frequency and channel estimation. And then based on those results, for each of these targets, we can do this delay and Doppler recovery and figure out those targets. And as a result, we'll also avoid this target masking, so that we actually find all these 3 targets that without this type of processing would be masked. Just to give you some quantitative idea about the performance, so it certainly leads a significant improvement in detection performance for this moving target here. So this curve here is called the developed method. So probability of detection is a function of SNR, and this is what you would, if you would do just regular 2D FFT process. And this figure just tells that you can actually resolve this target that would be otherwise invisible, but I won't go into detail into explaining what's happening there. So the other impairment we've been working on is how to exploit phase noise, and this problem is basically applicable to monostatic OFDM radars, so that where the transmitter and receiver are in the same location. In this monostatic setting, the phase noise will be actually self-correlated, and that correlation structure depends also on the range. And what we have done is we have kind of established the statistical properties of this phase noise in this self-correlated scenario, and then the idea is to kind of exploit this estimate this phase noise and track it, and then also exploit it for improved performance. So here are the equations, but I won't go into detail in those equations, but I try to again convey the idea. So in terms of these phase noises, they of course depend also on the oscillator models that is being used. So we have considered both free-running oscillators and phase-locked loops. And since this phase noise will have this range or delay-dependent covariance matrix, we have kind of characterized that covariance matrix, and based on that derivation, we have derived then a hybrid maximum likelihood and maximum a posterior estimator of the deterministic delay Doppler parameters. Then in order to estimate and compensate for the phase noise, we have developed an iterated small angle approximation algorithm that iteratively refines this delay Doppler phase noise estimates. And it has a very nice compact closed form expression that is updated. And then simulation results that I will show, then they kind of indicate that very fast convergence of this algorithm to the hybrid grammar. Hybrid comes from the fact that our objective is a mixture of maximum likelihood and maximum a posterior estimator. So there's both a deterministic and Bayesian component in that objective. So here's how this phase noise tracking or iterative estimation works. So then in this orange curve, it's basically perfectly, the blue curve is the first iteration, and the orange curve is after last iteration. So it's a very tight track of this actual phase noise there. And as a result, we can then kind of mitigate this phase noise because you have a very good picture of how it behaves. And then once you have kind of mitigated that, then you can. So what's the problem there?
It's okay.
Okay.
It's okay now. Yeah.
Okay. All right. So anyway, and then also we can actually get very close to the primary raw bound in the estimation, the range estimation, because we take advantage of this knowledge of the range-dependent phase noise covariance matrix. All right. So we do both kind of mitigation and exploitation, and the exploitation takes place in this for example, the range estimation. So we can actually hit the primary raw bound here in the range estimation. So I didn't describe the equations in great detail, but I hope I was able to convey the basic ideas how we do these things. But for those who would be willing to go through this detailed derivation and getting deeper understanding of all these equations, so I have listed some of the key references that we have written on this topic area where you can find the gory details of the derivations. Then it's time to wrap up. So I'd like to just conclude that of course, multi-carrier waveforms, they are used in most current and emerging wireless communication systems, and they are and will be employed in radars as well. And they have a very high potential for ISAC waveforms, and not only because of the signal processing and performance point of view, but also because a lot of the wireless hardware and so on is designed for multi-carrier systems and multi-antenna systems, and this could also exploit these hardware designs and the RF convergence that is going on in the hardware and circuit design community. These waveforms, there are certainly a lot of different design options depending on the tasks at hand, and also there are a lot of degrees of freedom that you can adjust to improve your performance, whether you are doing it through optimization, learning, or just pure co-design of these systems. The drawback that remains here is the high peak average power ratio that may limit the sensing range a bit. We presented some structured optimization and model-based reinforcement learning examples that used multi-carrier waveforms and optimized those waveforms and adapted them into changing channel conditions. Since multiple radios are working in the same and radio systems are working in the same spectrum, either cooperating, co-design, or just coexisting, interference management is very crucial. And we presented one example based on interference alignment that would allow you to kind of communicate and sense almost in interference-free channels, and the price you pay that you will use some of the degrees of freedom for that alignment performance. And finally, the idea that a lot of the drawbacks and impairment that wireless communication engineers hate and get a headache when they think about those things, they can be actually used for the radar purposes. So one should see the class basically half full instead of being half empty, and try to exploit these non-idealities and impairment for the benefit of radar sensing. So one can kind of flip the coin around and try to exploit those things that are usually considered to be drawbacks and so on. So this concludes my presentation, and I think it's time for our next speaker to present his most recent findings. So thank you so much for your attention, and I'd be happy to entertain any questions after this presentation is over.
Many thanks, Lisa. I think so. We get a number of questions. I think we still have we can still use 3 to 5 minutes to answer these questions. So
Okay.
yeah, so most of the questions come from Ahmed Bazi. So Ahmed, can you please unmute yourself and you can ask the questions by yourself.
Yes, thank you, Fan Louis. Thank you, Professor Visa. That was a very interesting talk. I have a couple of questions. First one being, given your work on IQ compensation and IQ imbalance and these kind of stuff, do you think IQ imbalance would have an impact on the whole JSAC system? And if so, does it make sense to include some constraints to minimize its impact, just like we do with PAPR and the constant phase constraint?
Well, the IQ imbalance, it's of course it depends a bit on also on the receiver structure. If you have a direct conversion or low IF or super head receiver, so it depends on how it behaves. But of course, that is also kind of impairment, especially because it will introduce some unwanted correlations between the I and Q component, and so it's not quite, and making this kind of signal non-circular, statistically non-circular. So it's not quite. I'm not quite sure if it could be exploited. I haven't thought it, but usually. That makes it a bit, especially in multi-carrier receivers, when you are applying FFTs and IFFTs, if the signal is non-circular, then it may have some unwanted effects and also cause this type of inter-carrier interference, so that the spectra will be overlapping, and then it would not be caused by Doppler, which would be, of course, Doppler and velocity. They are important parameters for the radar part, because they are directly related to velocity, but now the impairment would not really convey information on any of the parameters of interest to us. But to be honest, I would have to kind of also explore this topic a bit and see that if it could be somehow exploited. But that is usually something that remains more or less stable. That you can handle these things through kind of calibration and so on, whereas this Doppler and so on change depending on the velocity and what's happening in your target environment.
Thank you. Yeah, makes sense. And I've got another question, if you may, if you permit.
Yeah, I'd be happy to answer. Yeah.
Thank you. So in terms of, you showed many optimization problems for tackling JSAC. I'm just wondering, how do you see trade-offs in the optimization between sensing and communications? Is it only via including a cost function that is radar, for example, maximize a certain beam pattern cost function, or a certain beamformer with some communication constraints, or vice versa, like maximize the capacity subject to some beam pattern constraints? And here for reference, I would like to refer to the work of Fan Louis and the other co-authors on the paper entitled Toward Dual DFRC, Optimal Waveform Design, where they have a weighting function where you can actually tune raw. There's a raw parameter, and the higher.
So, right, I mentioned this like a Pareto multi-objective.
Exactly. Yeah.
So that's of course also a very good way, and that's a very good paper that you mentioned. But of course, then if you need to have a quantitative performance criteria, then this weighting may be hard to find this weight. For example, if you really want to guarantee constant false alarm rate for your radar detector, or and so on, then adjusting this weighting parameter may be very difficult. And then kind of linearly combining a weighted combination of, for example, criterion related to data rate and another criterion related to Kramer-Rao bound. So it's how to kind of combine those things. Of course, some criteria like mutual information, if you're using mutual information in both, just mutual information between different things, that might be easier to combine. But anyway, that if one finds a good way of weighting these things that you can guarantee certain performance for both subsystems, I think that would be that's a great idea, and that's a really nice paper to mention. Yeah.
Thank you. And one last question would be talking about CRBs and different metrics. In terms of metrics and performance bounds for JSAC, does it make sense to optimize jointly the CRB with along with the sum rate, or would there be another information theoretic bound between both subsystems? Is there like yeah?
Well, of course, CRB is basically related to parameter estimation, and that of course that objective would be used if your task is to estimate optimally target parameters. So, for example, target bearing, acceleration, and so on and so on. That if you need, or you could think of also the target as a rich scatterer, and you have to estimate target impulse response, because it might be you could use it for example, target recognition and so on. So if you need to estimate that parameter optimally, then of course CRB would make sense. But then of course how to combine, for example, Shannon-Hartley formula with CRB might be it's not necessarily straightforward. There's some work on the relationship between mean square error and Shannon formula by Sergio Verdu and some of his students. Okay. But that connection is we try to investigate, and we're not really able to use it that well. But there's some really fundamental information theoretical work on that area that if you are able to use it, so that would be very, very useful, because then it would allow you to use this information theoretic bounds for both the communication and the parameter estimation part.
Okay, thank you very much. It was very helpful. Thank you.
Okay, thank you very much, Vesa, for your very nice and informative talk. And some of our audience is asking if you are able to share the slides. So
yeah, I will send you. Yeah, I will send you a PDF copy of the slides. But
okay.
And again, I'd like to thank you and the organizers that this is a really fantastic seminar series, and I'm really happy I was able to share some of our ideas and work on this topic area. So thank you so much.
Thank you. Okay, so we'll have our next speaker. So Professor, let me share my screen first. So our next speaker will be Professor Ahmed Alkhateeb. So let me briefly introduce Ahmed to you. So Ahmed Alkhateeb received his bachelor and master degrees in electrical engineering from Cairo University, Egypt, and his PhD degree in electrical engineering from the University of Texas at Austin, USA. And so after the PhD, he spent some time in the Facebook. And after that, he joined Arizona State University, where he's currently an assistant professor. And his research interests are in the broad areas of wireless communications, signal processing, machine learning, and applied math. So he's a recipient of the 2012 MCD Fellowship from the University of Texas at Austin, the 2016 Naturally SPS Society Young Author Best Paper Award, and the NSF Career Awards 2021 to support his research on leveraging machine learning for large-scale MIMO systems. Okay, without further delay, let's welcome Professor Alkhateeb. And Ahmed, please, the screen is yours. Please go ahead.
All right, thank you very much, Fan, and all the organizers for the invitation and for organizing these interesting seminars. And okay, let me share my screen. Right, do you see screen?
Yeah. I can see it very clear.
Okay. All right. So thanks everyone again for attending. And so in this talk, I'd like to basically give our kind of understanding of this interesting topic of sensing aided wireless communication, and how we see the role of sensing, and especially multimodal sensing and machine learning could help in future wireless communication systems. Right, so let's start with the motivation. Side, okay. So let's start with the motivation. So if we look at the current communication system, so there are a number of key trends. Two of them are the use of large antenna arrays. So we continue increasing the number of antennas that we are deploying at the infrastructure and also at the different UE devices, both at low frequency massive MIMO or millimeter wave terahertz MIMO, cell-free massive MIMO, intelligence services. So different sources, different sorts of deploying large antenna arrays, and this will just continue to grow. So the main way to increase data rate in the future, in my opinion, is to just keep increasing the number of antennas and going to higher frequency bands, which is the other key trend. So the other key trend is that again, we're going from lower frequency in before 5G to millimeter wave in 5G, and potentially sub-terahertz in 6G and beyond. So now, as we increase the number of antennas and data rate and frequency bands, going to higher frequency bands, so these two key trends are mainly driven and motivated by the demand to achieve higher data rates. So we want higher data rates, so we deploy larger antenna arrays, get more multiplexing gain, or go to higher frequency bands and to access more bandwidth to again get higher data rates. Of course, there are other benefits as well, but higher data rates probably is the main kind of motivation to go to these larger antenna arrays and higher frequency bands. But then with these two key trends, number of challenges start appearing and becoming very critical. So two of them, again, or two sets of these challenges that come again with these two key trends are, if we first look at the use of large antenna arrays, so now we have larger channel matrices, narrower beamforming vectors. We need to align and estimate, train channels, training and feedback, and this requires a lot of training and feedback overhead, which makes it hard for these systems to support highly mobile applications, and also increase the power consumption at the UE, especially at the UE side, and puts challenges on the battery life. And if we look at the other key trend, the move to higher frequency bands. Now, at these higher frequency bands, the signal propagation experience high penetration loss, and also diffuse scattering. And this makes the signal or the communication lengths more dependent on line of sight, where blockages become a big challenge. And this makes it, again, hard for these systems to support millimeter wave or terahertz or sub-terahertz communication lengths with high reliability. So reliability becomes a key challenge, and how to ensure that this link, let's say, will not be suddenly disconnected because of moving blockage, for example, is a key challenge. And also, if the link is disconnected and the user needs to reconnect to another base station or to switch to beam recovery, let's say, to failure recovery to another beam, then this is typically associated with high latency. So reliability, latency become also challenging in these higher frequency bands. So now, if we look at these two sets of challenges that come again with these two key trends, then you can broadly say that these two sets of challenges originate from the channel acquisition or the difficulty to acquire the channel. Or in other words, you can say that acquiring the channel knowledge, if we have a way to acquire the channel knowledge with very low training overhead or for, let's say, free in terms of wireless communication resources, then we would probably have a way to overcome these challenges. For example, if we know that the channel, if both the base station and the UE knows the channel for, genie-added kind of channel acquisition techniques, then they will know where to point the beam. They will know how to design the precoding and all the associated functions, so we can support highly mobile applications. Also, if the UE knows a channel for free, then maybe it doesn't need to do continuous measurements and beam training, and will save the battery life and will extend the battery life. On the other side, also, if we look at even the blockage associated challenges, if we have now, if both the infrastructure and mobile users know the channel, not just in the current channel, but also the channel in the future, then they can potentially proactively predict that a blockage will happen before it actually happens. And then if we know that, then probably they can do proactive action. So for example, they can decide to proactively switch to another beam that will not be blocked, or they can decide to hand off to another base station in a proactive, low latency way. So acquiring channel knowledge for free or with low training overhead is a key way to enable or to overcome these challenges. And here comes, I think, the motivation for machine learning, or the key motivation for machine learning. So how can machine learning help in this channel acquisition, low overhead channel acquisition? So to get some insight, so let's start with the very general intuition that channels are defined by the various elements in the environment. So if you have for example, base station, UE, and the channel between them are defined or is defined by the different elements in the environment, including the environment geometry, the materials, and the electromagnetic characteristics of these materials, the locations, of course, of the transmitter receiver, the different scatters in the environment, the shapes and patterns and orientation, and so on. So intuitively speaking, if we can probably write this channel vector as a function of all these different factors. But of course, this is hard to characterize analytically and changes from location to location. Then here comes one motivation for machine learning, is to basically have a machine learning model that learns how to learn and approximate this function. This function that maps the different elements of the environment, including the geometry, the materials, the locations, etc., to the channel vectors, matrices, beamforming vectors, and so on. And the key trick here is that if we have a way to acquire these inputs or some good features for these inputs, for the environment geometry, materials, locations, etc., with low training overhead, then using this machine learning model, we can map these features that again could be acquired with low training overhead to channels or beamforming vectors, so on, that would require high training overhead. And this would be, one interesting way to leverage machine learning to overcome these critical challenges. Now, interestingly, as we go to these two, or if we look at these two key trends again, the move to higher frequency bands and large antenna arrays, then while they bring these new challenges on channel acquisition, reliability, latency, etc., they also bring some very interesting aspects. So one key aspect is that channels, as we go to higher frequency bands and large antenna arrays, become more and more dependent on the geometry and the locations of the user and the blockage and so on. So basically, the information about the geometry and the specific locations and orientations of the transmitter, receiver, and different elements in the environment become very useful in learning this mapping, or in other words, it becomes relatively, I would say, easier to acquire some good features to represent these inputs. And these features could be very useful, especially as we go to higher frequency bands and larger antenna arrays. So it's kind of an interesting, observation, I think, is as we go to higher frequency bands and larger antenna arrays, they bring new challenges, but also at the same time, they make the communication system more dependent on the geometry and locations, where we can probably leverage that to address the same challenge that they bring. And here comes basically the motivation to, if we have knowledge about the position, geometry, mobility patterns, etc., then this information could probably be very useful to address these challenges. And from here comes this general vision of sensing-aided wireless communication or multimodal sensing-aided wireless communication, where various types of sensors from wireless receivers as sensors to radar, LiDAR, camera, GPS, position, IMU, and all different sorts of sensors that are deployable at the infrastructure units and also at the mobile users. And if all of them collaborate to acquire awareness and information about what is happening in the communication environment from the positions of the user and different scatters and the shapes of these different scatters, their mobility patterns, and so on. So real-time awareness about what's happening in the communication environment, then this awareness could potentially be leveraged for the network can leverage this awareness to make quick decisions on, say, beam prediction, block prediction, identify, say, where is the best non-line of sight pass and reflector, proactive handoff, proactive resource management, user scheduling, and so on. So in a way, basically, this awareness could be a key for overcoming these challenges that come with these two key trends in communication systems. All right, so next, I'll try to classify these different sensors or environment sensing sensors to two classes. One is, I'd like to call it wireless communication receivers as sensors. So the antennas and the channels that we acquire through these antennas, or different wireless communication information that we acquire through these antennas, they also carry a lot of information about the geometry and the propagation characteristics. So we can potentially leverage this information also, or implicitly or explicitly, to help in as features that we can feed to these machine learning models that would learn how to map these environment geometry information that are implicitly or explicitly captured in these features to the channel information. Then here comes the question: why would we use channels to acquire channels? So I will clarify, and how can this help? So I will clarify this in a minute, in the next few slides. But before we go there, so the other type of sensors, just call it non-communication sensors, basically all the other kinds of sensors that are not the wireless communication. So from radar, LiDAR, camera, position, etc., which again, they can help in acquiring a lot of awareness about the communication environment, and this awareness could potentially be leveraged for the same reason. All right, so in the next few slides, just 2-3 slides, I will highlight very briefly why wireless communication channels could be very interesting way, or leveraging this, or could be interesting features for the geometry, and could help in this channel acquisition overhead. And then we'll spend the rest of the talk on talking about this multimodal sensing, more on the other types of sensors. So wireless receivers as sensors, to kind of understand or to capture the advantage that we think is there in using receivers as sensors for the objective of channel acquisition. So we derive or define this concept of channel mapping 2019. And essentially in this channel mapping, what we are saying is that if you are given a deterministic environment and there are two sets of antennas, M1 and M2, that are communicating with the same mobile user, or the mobile user could communicate with the two sets of antennas, then if we know that channel at the first set of antenna, we can map this channel to the second set of antenna, even if this other set of antenna is at a different frequency band or in a different location in the same environment. And there is kind of a simple proof for that. I mean, if we and there is a condition, of course, for this to happen. So before going into the details, like you can check the paper for like more kind of formal proof. But the key idea here is that if we define two mapping functions from the positions from the set of positions of the user to the channels at the first set of antenna and the second set of antennas, and then if we make this assumption, so and this is the only conditions that we needs to be satisfied, which is that the channels, which is the mapping between the positions and the channels at the first set of antenna is set of antennas is bijective. So basically, any two positions will lead to two different channels at the first set of antennas. So if we guarantee that this condition is satisfied, which in practice it is satisfied with high probability if we have relatively reasonable number of antennas. So I think 6 or 8 antennas in a reasonable communication environment. And of course, it depends on how many multipasses we have, what's the geometry of this antenna array and the frequency band, etc. But then if there are some papers also that kind of justify and go over this condition in detail. But the observation there is that in classical and typical wireless communication environments, this condition will likely be satisfied with high probability, at least. And if this condition is satisfied, this means that the mapping from the positions to the first set of antennas, the chance of first set of antennas is bijective, means that the inverse mapping exists. So if we know that channels at the first set of antenna, we can, there is mapping that maps these channels to the positions, which is, by the way, the main also conditions that we need in inverse in fingerprinting based localization. And then from, so we can map the channels to the locations, and then from the locations, we can use this second mapping to go directly to the channel at the second set of antenna. And then if the two mapping exists, then we can, the composite mapping exists also. So we can go directly from the channels at the first set of antennas to the channels at the second set of antennas. So this just proves that if this condition, if this again bijectiveness condition is satisfied, then this composite mapping exists, which means that we can go from the channels at the first set of antennas to the channels at the second set of antennas. Now, why this is interesting? The interesting thing here is that we didn't need to, I mean, through this proof, we didn't need to put any constraint on the frequencies of the two sets of antennas. And we didn't also put a constraint on how, let's say, far they are from each other. Of course, they need to be used in the same communication environment, but they don't need, let's say, to be co-located. And this means, well, this means that we can potentially, let's say, use 4-8 channels at sub-6 gigahertz band, which the channels are easier to acquire at low frequency bands with a few antennas, to acquire some information about the environment geometry and locations, etc., implicitly. And then we map these channels to the with machine learning. So if this mapping exists, and using universal approximation theory, there exists complex enough neural networks that can learn this mapping. So if we know the channel at sub-6 gigahertz with a few antennas, we can potentially map this knowledge to a millimeter wave beamforming vector, for example. That is harder to acquire. Or if we know that channel, let's say in uplink massive MIMO, which is again easier to acquire, we can potentially map this knowledge to the downlink FDD massive MIMO channel, which is harder to acquire and requires a lot of training and feedback overhead and so on. So this kind of there are different ways to leverage basically this channel mapping concept, but essentially the key idea here is that since we can acquire some channels that provide some awareness about the environment and geometry, etc., implicitly, and if there is a way to map this channel knowledge to the channels at larger antenna arrays, probably higher frequency bands that are harder to acquire, then using channel mapping, we can achieve that. So to be able to acquire the large channel, again, matrices that are harder to acquire using low channel matrices, low dimension channel matrices that are easier to acquire, potentially at lower frequencies. So I will not go over this, but in detail, but essentially, if you're interested, so there are some papers we talk about different applications from, say, mapping the channels from sub-6 to millimeter wave with more formal mathematical proofs, how to go from uplink to downlink in FDD massive MIMO, which is kind of a key challenge. Another way to look at it is this channel mapping in space. So if we have an FDD massive MIMO system with, let's say, 64 antennas, so we can potentially train and feedback only a subset of these antennas, and then use the channels at the subset of antenna to acquire the channel, to extrapolate using machine learning and acquire the channels at the other sets of antennas. Or and we have used this concept also in reconfigurable intelligence surfaces. So if we have probably a few thousands of elements, of passive elements, then that are very hard to acquire the channel for. Then if we embed a number of sparse sensors, sparse channel sensors in this RIS, then we can get the channels at the sparse sensors, and then use some machine learning way to extrapolate and predict the channels, or probably the beam directly for the full arrays in this IEEE Access paper. And so you can keep thinking of like different ways, interesting ways to leverage this channel mapping concept. Now, of course, all what I mentioned so far assumes deterministic environment. Now, if the environment is moving and dynamic, then in my opinion, it's hard to acquire, to become impractical to acquire exactly the channel matrix, but then we can potentially acquire some statistical knowledge about the channel. So for example, we can use a sub-6 GHz channel to predict the top 3, 4, 5 beams at millimeter wave, reducing the training overhead from, you know, maybe a few tenths of beams or more to a few beams. Or we can probably predict the channel covariance at massive MIMO downlink instead of predicting the exact channel, and then still use this dominant subspace to go back and reduce the number of training and as a training and feedback over. So there are different, I think, practical ways to take this to more realistic and while still using machine learning to reduce the dimensionality of the problem, and use classical solutions to fine tune and obtain the final channel and beam information. All right, so with that, I will move to the second part of second class of sensors, which is the main focus of this talk. Is really, if we go really beyond wireless communications or receivers as sensors and look at all these other types of sensors such as radar, LiDAR, camera, GPS, positioning, and so on. And how can we leverage all this information, and how realistic is it to leverage all this information to help in this, again, channel acquisition problem and its relevant challenges. So to start, I think addressing these interesting directions is first like to refer to some early research results that try to get initial insights about different pieces of this vision. So the first, I think, modality that could come to mind is position, right? So if we know if the infrastructure, let's say, knows the position of the user, then it could potentially leverage this position information to design the beamforming vector, especially in line of sight conditions. So this motivation it's captured in some of the early work, I think, on position-based beam prediction, which is, of course, a very interesting way to reduce the training overhead in these high-frequency large antenna array systems. And it is relatively simple to acquire. It's simple to maybe can design simple machine learning models to use this position information to predict beams or maybe channel covariance as well. But then it has also a certain number of limitations. As we go to indoor, maybe it's harder to obtain locations information. Location information itself also has a lot of noise, and I will discuss this in a few slides. And then another big challenge is that this position information may be mainly useful in line of sight. Now, if we start having different sorts of non-line of sight conditions, then there will be a lot of ambiguity in this location information. So if we know just the location, this is not sufficient to necessarily predict the right beam in non-line of sight condition, right? If we have different kinds of scatters between the base station and the mobile user, then every type of or set of scatters could mean different beam alignment pair. So we probably need more information than just position. Probably still use position and augment more side information. So another class of sensors is of course radar, which I know this community is interested in. So there is also early work on radar. So if we have some radar maybe deployed as the infrastructure, then we can leverage this radar information and the back scattering or the echo and the reflection from different mobile objects to position and to know the range and angle of these different objects, which could potentially help also in beam alignment. Can probably extract the parameters of these mobile objects and use that to reduce the beam training overhead. And then there, the questions that comes here is how scalable this radar approaches could be. If we just rely on radar with reasonable number of antennas, would this be realistic in dense deployments? So it's maybe, like maybe a street with tens of vehicles moving, or so this is a question that drives research, and it's interesting to answer. And in fact, I will not answer this question till the end of the talk. I don't know the full answer of this question, but it's just a question that is kind of interesting to think about and to explore. And this is one of the motivations of the data set that I will present in a minute. So another way to think about these sensors or another class of sensors is visual sensors. So if we cameras basically, and different kinds of visual sensors. So here we in 2019 start thinking about, can we just use visual sensors, so cameras, and to help this wireless communication, the specific set of wireless communication problems as we go to higher frequency bands, large antenna arrays, this beam alignment problems, blockage prediction, and so on. And the motivation here is that as we go to these higher frequency bands with larger antenna arrays, then the lengths become shorter and more line of sight, where visual sensors could probably be useful, right? So the infrastructure can probably literally see the mobile users and know where to point the beam. It could also, if the infrastructure has a camera, then this information, this visual scene understanding information, could potentially help in identifying where is the mobile user and where is other moving scatters in the environment, and could potentially predict, let's say, that this line of sight link is going to be blocked before it's actually blocked, and enable the proaction, enable the network to make some proactive decisions on how to manage the resources, how to switch the beam, how to handle the user, and so on. And there are other interesting applications that we can think of also along this line of vision-aided wireless communication. Another important motivation here is that if we start thinking about leveraging cameras or visual sensors, so these are very cheap sensors that are already deployed in many mobile devices, from autonomous vehicles to drones to AR, VR, and so on. So potentially leverage this information. And interestingly, all these applications, they are interested in high data rates, going to higher frequency bands, can potentially leverage these visual sensors that are already deployed there to also help the communication systems. And you may also think that deploying or adding or augmenting cameras at some infrastructure nodes with some privacy constraints could also be interesting. And this, of course, a topic that needs further discussions. So in order to do any progress in this research, so if we want to see how feasible using these visual sensors, or even the other classes of also sensors, how feasible these solutions could be, and to actually develop and benchmark and anything in this direction. So we need a data set. So for that, also in 2019 and 20, so we developed this data set called ViWi Vision-Aided Vision Wireless data set. And the idea here is to have basically coexisting wireless and visual data, where we build the same 3D environment. It is a synthetic data set. We built this environment in accurate 3D ray tracing as well as accurate game engines. And we generate the two classes of data: wireless propagation data from Wireless Insight or other accurate ray tracing models and emulators, and accurate visual data from or realistic visual data from Blender or other types of game engines. And now if we have this two coexisting, again, and this coexisting point is very important. So you want to see, you want to extract that channel information at the same point that you see this visual scene or this camera image. So this coexistence is a very important point. Now with this coexisting data from multiple sensors, we can start thinking and studying some of these interesting problems. We extend this ViWi later on to add LiDAR as well, and position, of course, information. So, and then using this data set, we started doing some very early initial, I would say, work on can we use this visual data using some ResNet 18, let's say modified ResNet 18 neural network to just predict the beam. So these are some initial results where the beam you see is the real beam predicted from this neural network that has just the visual scene as an input. So it doesn't have any other inputs. And we show that okay, we can get maybe 90-something% accuracy in this beam prediction task. It's, again, very simple task. And I will comment on it, of course, and how realistic this is in a second. We also extend this to, let's say, problem like blockage prediction. So if we know the beam information as well as the visual data, so can we use this to predict if this line of sight link is going to be blocked or not in the future? We show some gain. But then the question that, of course, we kept facing is, okay, this is interesting, but is this realistic? How can we realize these gains in practice? And can we really extend these solutions to real sensors and how the quality of the real sensory data affect, how much will it affect the performance of these solutions? So, for example, if you go to dark light or dim light conditions, will visual sensors still be useful? If we go to realistic GPS information, I mean, will the noise in this position data be sufficient for beam alignment? So all these kinds of questions on the radar information, if we look at radar sensory data with all kinds of noise, then will we still be able, and low resolution will still be able to do this beam alignment efficiently, for example, or blockage prediction, all these kinds of interesting applications. And then how about latency? If we, if you start thinking about these different sensors that are not communication sensors or not antennas, so they run typically in a different time scale than the communication. So in communication, we talk about milliseconds. Here we can probably talk about tens of milliseconds. Then between the acquisition latency to the processing latency to the inference latency, then is this, will leveraging all these sensors be still realistic and useful with all these limitations, or are these kind of a critical bottlenecks? Will these solutions scale to multi-object scenarios? So I just showed you this simple case where you have one vehicle moving in front of the base station, and then we use this visual image to predict the beam. But then this is, of course, have just one vehicle. Now, if you have multiple objects moving, how will the base station distinguish which one is a user and which one is just other objects moving? How much data is needed to train these models, and how about transfer learning, and a lot of other questions. So in order really to take all this vision and these ideas to one step to realistic, let's say, or the real world, then we again need to have a data set that's based on real world measurements with realistic sensors, and to have this, again, this point of coexisting data from different sensors and communication. So with this motivation, we started building this so-called deep sense. It's a large scale real world multimodal sensing and communication data set. Okay, so we started building this data set more than actually 3 years ago, almost around the time where we had this YY data set, and we started getting these questions about how realistic these solutions could be. So we said, okay, can we start, collecting real data and see if these solutions will actually work on real data. So we started building this multimodal data set with different communication, with different data modalities, from communication, in particular millimeter wave, beamforming data, radar, IQ sample, slider, camera, position information, and so on. And we try to address different communication scenarios. So from V2I to RIS to drones to to pedestrian moving and to outdoor or outdoor and indoor and so on. And then we clustered this data in scenarios, and in a very standardized way, the way we define the scenario and the data and the testbed, so that we can keep scaling this data set in the future as we, to cover more and more use case and to be more and more useful data set. So far we have almost 1 million, actually more than 1 million data points. These are multimodal data points. So every one of these data points has multiple modalities from beam training. Not all the data has all the modalities, but every scenario we have certain number of sensors. So we have certain multimodal data in each scenario, and so we have so far more than 30 scenarios, from vehicles to humans to drones to robots, and a more kind of controlled environments, indoor and outdoor. And we try to make it as realistic as possible from elevated base station kind of conditions to have also enough variance in the data set, from user speeds to distances to power to indoor and outdoor and so on, different kinds of streets, different orientation. And so it's essentially to make sure that it mimics realistic deployments as much as we can. And then, which is, in our opinion, is the key to enable really this, studying this machine learning problems, from generalizability to scalability problems and machine learning. And so far we have more than 1 million data point, again, with different data modalities. For radar, we have IQ data, camera RGB images and depth images for some cases. We have both 2D and 3D LiDAR now in some scenarios, as well as accurate position information, both outdoor using GPS, accurate RTK GPS, and indoor using other stand systems. So now with this data, again, as I mentioned, we try to cluster this data in scenarios, so that every scenario is a basically data collection session. And this is again a way to kind of make sure the data is organized and also offered in a simple way to use and well defined. So this is a sample of one scenario where we have position information, visual RGB image, and beam training power, millimeter wave beam training power, LiDAR, radar, and we have almost this kind of visualization for every scenario to make sure also this can be probably useful in debugging the data and ensuring that results make sense. So now with this deep sense data set, think that it can enable a lot of interesting applications in both in wireless communication, such as using sensing for communication and beam prediction, tracking, block prediction, and so on, as well as some sensing functions, positioning and ranging, imaging, detection, classifications. We're also adding more and more scenarios as to cover more and more important use cases. And then kind of the main goal actually of this data set was to enable the machine learning questions, study machine learning in terms of all these interesting questions in future learning, data fusion, transfer learning, generalizability, model scalability, and so on. So we hope that this data set would be a good step towards facilitating these interesting directions. Now, in order to also make sure that this data set will be simple will be reproducible and will enable benchmarking, which is a key again to kind of increase the make all these development efforts of all the community, right, and research really as useful as possible, I would say. It's important for these machine learning specifically solutions to be reproducible and to have a simple way to compare results and to benchmark and kind of really following the standard in machine learning community. So in order to do that, so we defined also what we call task-specific data sets. So we looked at kind of the important, let's say, machine learning tasks: beam prediction, current beam prediction, future beam prediction, block prediction, and so on. And then we'll keep adding more and more tasks. And then for every task, we define task-specific data sets. So it has training validation tests with certain inputs and outputs that are sufficient to study this task, so that basically this makes sure that everyone is comparing, is developing and comparing based on the same ground. And then there's this, encourage basically people to also submit the results to kind of enable, again, benchmarking. And what we really hope is that if anyone is, is using this data set to develop something, then please send to us, and we will add your paper to the DeepSense website, make sure more people are can compare with your results and your code, and to make all this kind of development more useful and straight towards the community data set. All right, so in the next few slides, I will try to discuss a few applications and that are enabled by DeepSense, and see how we can probably get some very initial insights about some of the questions that I kind of posed in the last few slides. So one of them is sensing aided beam prediction. So if we can use these different sensing modalities to predict the beam, and again, if we can do that, then we can potentially massively reduce the beam training overhead. So instead of, let's say, searching over 64 beams at infrastructure, if we have now beam alignment or if we have antenna arrays at both the base station and the UE, probably we have hundreds of possible beam pairs. Now, instead of doing all this exhaustive search, can we just rely on some sensors to at least reduce the dimensionality of the problem? Instead of searching over hundreds of beam pairs, we can maybe look at a few or something like this. So that would be a great benefit in real world. And now that we have real world data sets, we can really study how, can develop your solution and test it on real deployment, let's say, or a close to real deployment, to see how practical these solutions are. So to study this, so we started with, we looked at a few, again, very initial cases and very initial results here, but there is a lot of, I think, way to go, and a long way to go, and a lot of interesting research questions that are open, and I will list a few of them, not a few, actually, I will list a lot of them in the next few slides. So one of them is position-aided beam prediction. So I mentioned that position is probably the most intuitive modality that comes to mind when we think about beam alignment, right? If we have a position, we can probably quickly predict the beam. But then how realistic accurate positions and how useful accurate positions are for this task. So to study this, we looked at 9 scenarios out of the DeepSense dataset, and we designed 3 different machine learning models, or adopt 3 different machine learning models: lookup table, k-nearest neighbor, and neural network. And then we looked at design different machine learning, so different kind of pre-processing and normalization approaches for this position data, to see, like, based on, let's say, latitude, longitude, or based on angle information and so on, how to predict the beam. And these are some results. And so without going over maybe everything, but essentially on the left figure, so we show the top K beam prediction accuracy versus the beam, so versus the K. So for example, with 3, if K equals 3, this means that what is the probability that the top 3 beams predicted by the neural network includes, or the machine learning model includes a ground truth beam. So now that we have also all the beam training, actually in the data, we have the exhaustive search beam training. So we have the ground truth. So we know the ground truth, and we can study how we can evaluate the system based on this ground truth data. So what we show in this data is that using this realistic GPS position, we can actually, if we just look at top 1, so what's the probability that the top or the first beam predicted by the machine learning model is the right beam? It's actually not in the 90s. It is 40-30%. So which is maybe 50 in the best case, so which was interesting. I mean, if you look at the position, it's very, it might be very intuitive that if you know the position, you should know the beam was high probability. But given the noise in the position data, and also in the beam, so the beam patterns themselves could be overlapping, could have some non-idealities in their shapes and so on, that would also add another, noise to the training data. So that the data that we use to train the machine learning model, so this data in itself is noisy in reality. So the machine learning model is basically trained on noisy data, and is also making, let's say, imperfect predictions. Now, however, you can also ask, so this is one, and I think, interesting point. Now, we can, of course, if we reduce the number of beams in the code block, we can expect better results. We have it's a simpler classification task. Now, if you, another important actually question to ask here is looking at accuracy, beam prediction accuracy, which is probably the most common metrics that we have been using and others in machine learning based beam prediction tasks. Is accuracy the right metric? And here we can argue that probably no. If the end objective is a communication, finally you want the communication system to perform, let's say, to have the best data rate or something, then probably looking at something like the power loss, how much power loss we have in this wrong beam prediction or let's say imperfect beam alignment compared to accuracy is probably a better metric, because it's more coupled and closer to the end objective of this beam alignment process. So here, if we look at power loss, even if we have 30 or 40 beam prediction accuracy, we are still within 2 dB, 3 dB loss compared to the ground truth. So which is not bad, I think, is and you know, like if you look at it then in this, from this performance metric perspective, which is probably a more realistic one from communication perspective, then you see that these results may not be too bad. And then this is again kind of maybe makes more sense for position. Now we can also look at other data modalities, for example, in radar. So in the data, again, we in this data set, we have IQ data for radar. So you can do, you know, all kind of interesting things in pre-processing and before you actually use just directly, let's say, neural network. And you can use all the knowledge in radar processing that's very rich to you know, to kind of simplify the problem, to extract reasonable features. So it's kind of a very interesting space for innovation and research and development to make these kind of you know, solutions as low complexity as possible, as fast as possible as well, and looking at inference and of course performance wise as well in terms of, let's say, beam prediction or block prediction and so on, tracking. So we looked at this again, obtained very initial results about the feasibility of using low resolution radar with only 3-4 antennas for beam prediction, and we found that using radar we can probably achieve closer to 90% beam prediction accuracy in top 5. So top 5 again means that instead of doing 64 beam training, we use machine learning to reduce this search space to 5 beams. And with guarantees that, and then we do refinement over the air to find the best beam out of this 5. So this, and then what is the guarantee? Basically, that best beam would be 1 out of this top 5 beams that are predicted by the machine learning model. So here's these results say that the best beam is within the top 5 predicted beams with more than 90% accuracy. We can also look at latency and complexity. And one observation here is that if we look at this radar-based machine learning solutions, then processing and inference time together could probably be less than 20 milliseconds, and which is probably not very large number. And latency is an interesting, of course, point that comes to you know, mind when we talk about, again, communication systems. And my opinion here is that probably these solutions, the sensing aided communication solutions, may not be very let's say, applicable for real-time inference, but you can, or let's say to predict the current beam. So take a snapshot and predict the beam within the coherence time. So it's within, let's say, 5-10 milliseconds. But they could always be useful, or could probably be useful for future or proactive or future prediction tasks. So for example, if we have a sequence of 8 or 10 radar maps for the past, let's say, 8-10 samples or coherence times while the vehicle was moving, then we can probably leverage the sequence to predict what would be the beam, the best beam to serve this mobile user in the next 4 or 5 instances. And then here we have more or more relaxed constraints on the inference time and on the processing and inference time. So probably 20 milliseconds could be useful and couldn't be a big problem for that object. All right, so another important question that is normally asked when we talk about sensing aided communication or multimodal sensing aided communication is it possible to scale for scenarios with multiple objects? Now, if you have just one moving object in front of the camera, then it's a very simple object detection task in machine vision, and we can just use this directly to learn the mapping between this object in the scene and in the visual scene and the beam, and it intuitively would work very well. So, but how about multiple objects? So if you have multiple objects and maybe multiple of them are moving, and how realistic this would be? So to do that, we would need to do another function on top of just object detection or simple, let's say, machine vision. We would need to do what we call actually as user identification or transmitter identification. So now we need to have one at least or more attributes for this mobile user, the communication mobile user, and then we would need some sort of fusion of this sensing, the main sensing modality, let's say, which is maybe RGB image or radar data, and this new attributes that of the user. So for example, it could be the position of the user in addition to the visual scene, and then this position and vision together, they would implicitly or explicitly do the two tasks, which is identifying which one out of these different moving objects is the user of interest, and then do the task of the end object, which is probably beam prediction here. So so in this paper, on these papers, one of them is on archive and another hopefully will come soon. We look at these problems, and we extend this also to radar and other modalities. So to kind of study this, how these solutions are scalable and feasible for more realistic scenarios. So here we develop this approach for where we look at position and vision, and then of course there will be a question why would position be sufficient or not, and we can discuss this. But then if we have vision and position, would we be able to really predict the beam in multiple object scenarios? So this is real demos that we have done using this approach. So here basically what we do is that this system relies only on visual data and position data, so no wireless communication at all. No wireless, so we don't use any wireless resources for the beam prediction. So we just use visual data and position data to predict the beam, which essentially means that we, zero beam training overhead, which as we see, like still performing well, and could be now scalable for higher frequency bands and larger antenna arrays. It's kind of an interesting initial, I would say, insights about the feasibility of these solutions. I would probably go faster here. So another interesting application is proactive blockage prediction. So can we use this different modalities to predict whether a blockage will happen or not in the future? So in the future, probably 100 milliseconds or 200 or 300 milliseconds. And then if we can do that, then this 100, 200 milliseconds are very valuable time for the communication system to make proactive decisions on the network management. So I would like just to kind of highlight this work that we have done on again, using one of the deep sense scenarios on using just N-band millimeter wave signals. So here we actually don't use LiDAR or radar or other like non-communication. So we just rely on communication sensors, just the channels that we measure or the beam training power more accurately that we measure through, let's say, the frequent beam training process in the communication system. And then what we try to do is that can we look at some pattern in this beam training map that would indicate that a future blockage will happen. So just look at beam versus time power map, and then we ask, is there a beam? Is there a specific pattern, maybe scattering pattern from this approaching blockage that would indicate that a blockage would happen in the next 100 to 100 milliseconds. And then if we can do that, then that's great. This is in-band sensors that wouldn't even need other sensors. So for that, we again collected data, so skip this. But essentially here, this just shows like an example of example sequence in this data set where we see this kind of pattern, which is actually a pattern scattering pattern for this approaching bus here to this communication link. And it happened just before the blockage. So what we basically are trying to do here is to leverage then these machine learning models that learns how to identify and extract these patterns and infers that the blockage will happen before it happens. And then we show that can use these to kind of get 80% or so accuracy in the blockage prediction. Again, this is one task that we have in this task-specific data set. So we have the specific data set and we have the result and the script as well that you can compare with and hopefully do better. And we show that we can also interestingly use this wireless patterns to not just actually predict if a blockage or not will happen, but also to identify the class of this blockage. Like, is it a car or is it a bus? So interestingly, just using wireless communication sensors, you can get some insights about even this question with some, again, initially reasonable accuracy. Again, there is big room for improvement, which is, I think, is exciting because it means that there is really a lot of research that needs to be done. And yeah, so we extended also this blockage prediction in other scenarios for radar lidar vision. Again, I mean, in my opinion, this work is very initial, a lot of room for improvement. So this is a sample where we show basically the sample of the data set where we have radar. This is beam power versus time and beam training. So this is a fixed transmitter, and then this image you see from the receiver perspective. And here you see basically different classes of blockages, from bikes to pedestrian to cars to buses, and kind of opens the door for a lot of interesting research on classifying blockages, which could be, by the way, very important for also network perspective. I mean, if a blockage, let's say we identified the blockage as a bike, for example, is it do we really need to do proactive handoff, for example, or maybe it's fine to wait for 1-2 milliseconds for this little blockage to pass, right? So, all right, so last 2-3 slides, I'll just go over some open questions. There are a lot of actually open questions for in this exciting research direction. So if we look at visual data, actually in every data modality we have a lot of questions, and then from machine learning there are a lot of questions, and from fusion there are a lot of questions. So I'm just trying to list some of them to kind of just shows kind of motivate maybe interesting research in this direction. So from vision data, few questions probably are like, I mean, is the camera practical range, like the range of the camera is typically 100 meters. So is it a limitation for this wireless communication systems? And can we maybe extend this range by having network of cameras or network of sensors that are jointly collaborating and to extend the range and to lock to the communication environment from different viewpoints? Can it still work well in low light and dark scenarios? And is it scalable to different weather conditions? Can cameras help in non-line of sight communication scenarios? So if we have blockages and non-line of sight, I mean, will it still be useful, or and somehow maybe can we predict, basically, if we know that the blockage, we know maybe the location of the user behind this blockage, can we use the visual data to identify which, scatter to point the beam to reflect the right direction based on the materials and the geometry and the visual scene understanding and so on, and based on the prior observation of the system in this location? So, so there are a lot of questions. So in this paper, we list, I say 10 open questions that we think are very kind of have high priority or kind of very critical, and require research and innovation. For LiDAR, I mean, if we think of LiDAR, so this is a very expensive device. If we really need 3D LiDAR, high resolution LiDAR, so then the question, and also area-wise and like size of the LiDAR, can we deploy this in realistically in let's say AR, VR or something like this. So then, I mean, if we look at lower resolution and lower cost, also LiDAR, such as 2D LiDAR, then it becomes interesting to see, is it sufficient to do these tasks using cheaper, lower cost, lower resolution LiDAR, and to do some interesting processing signal processing actually plus machine learning in these directions. How to go from end to end, from LiDAR to the final end objective in communication system is also an interesting open research question, in my opinion. And if we look at position, then we draw some very initial insights again on position-aided beam prediction in terms of noise, and we didn't find very good results. And there is really a room for better designs here, and the better processing, denoising, maybe position denoising, and then how to really look at the value of positioning in non-line of sight scenarios. And radar, how many antennas do we need to have reasonable performance? Is it scalable to dense deployments with multiple objects? How about fusion of these different modalities? So every modality has different advantages and drawbacks. And then if we want to fuse, and interestingly, many devices have already multiple of these sensors. So autonomous vehicles, they have maybe camera, radar, LiDAR, and so on. So probably the sensors are there. And then the interesting question is, from complexity, latency, performance, and so on perspective, I mean, is it interesting to fuse all this data for a particular wireless communication task, or probably we should select maybe one based on the scenario? Is it indoor versus outdoor? Is it in dense deployment versus, or in dense scenario versus lower, less crowded? Is it line of sight versus not? So again, I mean, there are a lot of interesting open questions in this fusion direction. And from machine learning now, and which is kind of one primary goal of this data set, is there are a lot of questions that really quite open in terms of how to design robust machine learning model and to deploy mismatches. We have different data sets, different scenarios in different locations and different orientations and so on. So we have, I think, sufficient variance in the data set that we can probably, community can start looking at some of these questions, and how much data set is needed, how much data is needed to train and refine, how often should we refine this machine learning model, how to design more estimated data, how about transfer learning, how about unsupervised, weakly supervised learning, and so on. Now, in particular for ISAC, I mean, one integrated sensing and communication, one interesting, of course, direction is to explore this different machine learning rules in this topic of integrated sensing and communication. For example, waveform design and resource allocation and self-interference cancellation and management. And then if we look at a network of sensors, okay, if you have a network of communication and sensors, then how about the interference, and how about this complex decision? So again, in this paper, we also try to one last thing I would say is, this is the last slide. So the goal of this deep sense is really to push towards community data sets. I just would like to kind of put this last slide for a call for collaboration. If so the hope here is that we keep growing this data set to cover as many of these directions as possible and to enable this research as much as possible. We have already started some collaboration with other groups to augment new scenarios, to add new scenarios for to enable waveform design for joint communication and sensing. And to add massive MIMO subset squares, massive MIMO data. So if you are interested in collaboration, please contact us. And with that, I will stop here. So if you are interested in looking at more details, so you can check the websites or Deep Sense website in particular, and our magazine papers and other papers. Thank you, and looking forward to your questions.
Okay, many thanks, Ahmed, for the very, very impressive talk on the sensing assisted communication. So we do receive a number of questions from our audiences. So I will ask some of them to ask questions by themselves. So I think the first question comes from Ahmed Bazi. So Ahmed, can you please mute yourself and ask a question?
Yes, thank you, Fan. And thank you, Professor Ahmed Alkhateeb. I just have a very small question. It's a very interesting talk. There's a lot of information. I have a small question, which is, do you think imperfect CSI would be a good scenario to consider in your settings that you got?
Sorry, perfect CSI?
imperfect
Imperfect.
CSI, channel state information. Would it be a good, let's say, system model, or to assume in your settings?
You mean to use sensing to predict imperfect?
Yeah, because you're assuming in your settings that we know the channel and we're predicting the channel to escape or proactively run away from blockages. So would it make sense to, do some performance analysis or derive some new beamformers given imperfect CSI? So when the channel is not perfectly known, it's given with some.
Yeah, of course. I mean, yeah, if I understand your question correctly. So in as part of the data set, so we also try to add CSI information. This is not yet in the current available scenarios, but we are working on this. So hopefully soon we'll add scenarios with CSI. So you can so measure CSI. So by construction, they are not perfect. So you can potentially leverage this imperfect CSI to study actually different wireless communication and machine learning problems in communication beyond also sensing. The other side of the story is that if your question is about predicting CSI, then my opinion, I mean, it's in general in machine learning, I think it might not be very practical to use machine learning models to predict actually CSI, I mean, final CSI. But because especially at large scale MIMO systems where machine learning is probably more interesting, because if you go to large dimensional MIMO systems and large scale MIMO, then the channel becomes very, very sensitive to little imperfection in the estimation. So the approach that I believe is more practical is to have a hybrid solution where you rely on machine learning to reduce the dimensionality of the channel estimation problem, and then use over-the-air classical refinement for estimating the channel. So this is a way where you leverage machine learning to reduce the dimensionality of the problem. So it's still very useful. Maybe get one order of magnitude less dimensionality or less complex problem, and then use over-the-air training to have a robust. So this is a way to, in my opinion, to have a practical, robust way for channel acquisition and CSI acquisition and using machine learning. So you can think of this as both sensing, or so you can use maybe this visual data to predict the channel covariance. We have a paper, I think, on this also. So we can predict visual data. We can use visual data to predict channel covariance, and then you can use channel covariance, maybe the dominant subspace of the channel, in massive MIMO to go and refine and extract, estimate the channel.
Okay, thank you. Yeah, that was partly my question. Thank you.
Thanks.
Okay, so our next question comes from Rizky Hesyan-Dika. So Rizky, can you please unmute yourself and ask a question?
Yeah, thanks for the interesting presentation. So I have a question regarding the millimeter wave blockage prediction. Do you think that the processing time of predicting the blockages in camera or radar plus deep learning or machine learning is sufficient for a millimeter wave system to perform the handover to an alternative base station or access points? Because we know that this using multiple sensors and deep learning introduces additional delays and require large processing resources.
Yeah, actually, yeah. So this is a very good question. I mean, excellent. I mean, so yeah, exactly. I mean, latency is definitely a question, and our initial results. I mean, so we have on the website. So we looked at some, again, very initial ways to do this proactive blockage prediction using radar, lidar, and vision, and we look also at inference latency and processing capture latency. So in general, what we see is that it's in the order of actually the inference itself is very fast. I mean, you can make, like, with some network quantization and pruning and so on, it could be a few milliseconds, which could be in itself very reasonable for even real-time prediction. But in the challenge in latency comes from data capturing. So capturing the data using either radar or visual data or lidar and so on. These are very would say slow in terms of it's running in a different time scale compared to communication in tens of milliseconds compared to milliseconds. So here, if you look at end-to-end latency from capture to inference, it's typically in, let's say, block prediction inference, it's typically in the range of 20 to 40 to 50 milliseconds. Now, this actually, I mean, now if you can predict the blockage, let's say 500 milliseconds before it happens, then, you know, like delaying this prediction by 40, 50 milliseconds will not be an issue, right? So if you take maybe you capture, you know, you capture a sequence or a visual scene or radar, and then you maybe take 40, 50 milliseconds to predict that a blockage will happen, you know, 400 more milliseconds in the future. So this 400 milliseconds is more, I think, more than sufficient time for the network to make decisions. You know, like network decisions are typically in the tens of milliseconds. So yeah, I mean, I think initial results, I would say, are, I think, very promising in terms of feasibility or to do future predictions and despite the latency of these sensors.
Okay, thank you.
Okay, so we have another question from Changsheng Yu. Changsheng, can you please ask the question by yourself? Hello? Okay, I think he may not be online. So he's asking how to design, customize a neural network for different channel mapping learning.
For different channel?
Channel mapping learning.
Channel. Yeah, so this is an interesting research question. It really depends on what exact problem we are looking at. So if you, for example, I mean, we looked at you know, is it a classification task, or is it a regression? Is local information in that channel is important? So maybe you can look at CNN kind of models, or versus maybe fully connected or less less intuitive networks. In some cases, if we are designing these models for systems with hardware constraints, such as maybe hybrid analog digital or analog beamforming architectures. So here it may need to look at complex valued neural networks, or even to design some of the first layers in these neural networks to account for the hardware constraints. Otherwise, actually, these networks may not be even deployable. So here the approach would be maybe to deploy part of this neural network in the phased array, or to look at the phased array or the hybrid analog digital architecture as part of your neural network. And to do that, you need somehow to model these first layers of the neural network as complex valued neural networks, maybe with unit modulus constraint, or so it's kind of even more constraints on these. So it really depends on, is it RIS with passive sensors or with passive elements? So it depends on the problem, and we have studied some of these directions in our papers, and others also have other big groups. A lot of groups looked at also other very interesting directions in this area. So
okay, many thanks. I think I have so myself will have a final question for you, I think. So comparing to the current, let's see, the 5G new radio standards, which adopt a reference or pilot signals to do beam training or beam tracking. So how much overheads can be exactly reduced by using, you know, your sensing assisted communication? So this is the first question. And the second one is, do you think that sensing assisted communication is able to eventually help us to bypass the general channel estimation procedure?
Yes, these are excellent questions. So for the first one, it's actually very interesting that some of these sensors could be added in a very transparent way to the standard. So if you use 3GPP, let's say 5G in our standard. So if you look at vision or radar, maybe radar is less maybe doesn't have privacy concerns or challenges. So if you augment radar to the base station, then it could acquire this knowledge, could identify the mobile users that the base station is communicating to, and it could just reduce the frequency of beam alignment, or it can maybe optimize the codebook, or to reduce the size of the codebook, right? So instead of, let's say in 5G and R, I think we have maybe 64 beams that this like an SSB synchronization beams that base station use, and the initial sounding. So maybe we can use this machine learning model to predict, okay, what are the best 4-8 beams that could be used. So I think a factor of 10 would probably be very reasonable in a transparent way to the communication system and to the standard. I have seen other researchers claiming, I think, more than this, but yeah, I mean, I think in the range of 10 or something is probably very reasonable with a transparent way. Now, if we start looking at end-to-end solutions where both the UE and the base station also, or the infrastructure, collaborate together to do something more smarter, then I think we can do even more. And I have seen also some interesting research where radar sensors, let's say, are used at the UE side, again, in a transparent way to the infrastructure, to standard, to just reduce based on the sensing, the environment around the mobile, just the handset mobile user, sensing the environment around it and the mobility and so on, could just decide that, instead of doing this beam training every 20 milliseconds, maybe we can do that every 100 milliseconds or something like this. And by doing that, it extends the battery life. And so I think there's really a lot that could be done, even in a transparent way to the standard. It could still achieve good saving in performance in terms of mobility, reliability, latency, power, battery life. The other point was on
so bypassing the channel estimation procedure.
Bypassing channel estimation. Yeah, I mean, so actually, yeah, I mean, as I was replying to the other question, that on the channel estimation, that in my opinion, I mean, different than maybe beam. So beam prediction, I could probably think that beam is a more like a statistical metric. It's a zone or a cone, or right, or where you don't need to be very, very accurate in beam prediction. But the channel is something that the complex channel vector or matrix needs to be acquired very, very accurately. So I think using machine learning to kind of directly eliminate the channel acquisition problem, I think may not be very, in my opinion, at least may not be very practical. I mean, what I believe is that you would probably have a hybrid solution where you can use machine learning to reduce the dimensionality of the problem. So for example, the base station can use machine learning models to say that, okay, I have 64 massive MIMO base station, but probably these 3-4 dimensional subspace is where 90% of the energy of the channel is. And then now it can design its pre-coding pilot, its training pilots to only focus on these 3-4 dimensions. And then this may reduce a lot the training overhead as well as the feedback overhead. So if you now look at the CSI compression, then this codebook could be actually a very simple codebook. It may not need to compress the full channel. It may have just very low dimension channel. So it may help in reducing both the training overhead and the feedback overhead. So it's kind of I think a hybrid solution where you rely on machine learning to reduce the dimensionality of the problem, and then you rely on classical over-the-air training to obtain the final channel information.
Okay, many thanks.
Thanks,
Professor Alkhateeb. Very good point. And we have received many queries about how to access your data set. So is it fully open sourced?
Yes, the data set is 100% open source. We have published, I think, more than maybe 20 scenarios so far with different modalities, and we have also published, I think, most of the development data sets in the beam and blotch prediction, in particular with radar. I made sure that this is published before this talk. So the radar aided beam prediction and blotch prediction development data sets are there, and And as I said, like we encourage people to kind of adopt this data set, to give us feedback, and also to contribute to the data set. So we have been collaborating with a number of groups on collecting data like jointly. So we can share our scripts actually that we use to synchronize the data and for the data measurements and data collection. We also really encourage anyone that uses the data set to send the papers to us, and we would like to list these papers on our website. So we'll have a directory for all the papers that are based on the data set as well from all other groups. So the hope here is that we would like to make this data set as really an enabler for several research directions and integrated sensing and communication, or integrated multimodal sensing and communication.
Okay, many thanks, Ahmed. I think that will be all for the questions. And with that, I would like to thank Professor Visa Koivunen and Professor Ahmed Alkhateeb again for accepting our invitation to present their fantastic works on this very timely topic. And so we'll have our next webinar in June, and we hope to see you again in our future events. Okay, so with that, I would like to thank both speakers again, and goodbye.
Thank you very much.
Well, thank you, and bye-bye.
Bye-bye.
Bye-bye.